Welcome. Today in this lecture we shall be doing some problems on the energy interactions in reacting system. So here we shall be using all the concepts we developed in our last lecture and check that how to implement those concepts in solving some real life problems. So first problem is on the concept of degrees of freedom, and this has been applied for a combustion process. In this problem, methane is burned with 5% excess air in a furnace. The stream composition and the variable values have been shown in this particular figure, and the process occurs with each stream at 1 atmosphere pressure. So we have to determine the degrees of freedom for this system. So here you can see this is a typical representation of the combustion of methane. Here we have a furnace and we are inputting the methane stream and the air stream, and as you can see that air is basically consists of nitrogen and oxygen, which are the major components of air, and here the pressure have been written and the temperature will be something arbitrary, but it is specified. Now after the methane gets combusted, there could be the production of carbon dioxide if there is a complete combustion, and if there is partial combustion there will be production of carbon monoxide. So you can see in the outlet stream we have carbon monoxide and carbon dioxide, both of them, and then it will also produce water. So here we have H2O plus some unreacted oxygen, and the nitrogen is remaining unreacted all throughout. So whatever nitrogen is going inside the furnace will be coming out of the furnace without any kind of reaction. But what changes will occur is this: the inlet streams will be having certain temperatures. Due to the combustion, the temperature of the outlet stream will be different from the inlet stream temperature. And here it has been shown the Q, that is if there is any kind of heat exchange between the furnace and the surroundings. With these information, now we shall be doing the degrees of freedom analysis to figure out whether this problem has been defined properly or not, so that we can solve for the unknown variables. Now first, as we learned that we have to first list out all the unknown variables. So here you can see that we have listed out the variables. So species in the F1, and there is, again I have shown for your reference this particular figure. So here we have only one species, so that is why we are counting only one. Then species in F1, this will be F2. So this will be F2 here. Okay. So this in F2 we have two species, that is oxygen and nitrogen. So we are counting 2 here, and in the stream F3 here you can see we have 1, 2, 3, 4 and 5. So we have 5 components and we are putting 5. Now please understand what we mean by these species in F1, F2 or F3. We mean that their composition. Okay. So how much of these species are present in each of the streams is given by their maybe mole fraction, maybe mass fraction, okay, or maybe some concentration in terms of say mole per cubic meter. So all those things are being counted. So that is what we mean by this counting of the species. And next we come to the total stream flows. Now here we have 3 streams, F1, F2 and F3. So these are the 3 variables. And then we have stream temperatures. So associated with each stream there will be one temperature. So we have 3 streams, so we have 3 temperatures. And then steam pressure. So we have 1, 2, 3 streams, so we have the steam pressure. And then the Q, that is the amount of heat that is going out of the system, that is the one. and extent of reaction. Now we have two reactions possible, as I just told you. So methane can react with oxygen partially to give carbon monoxide, or it can also react with oxygen completely to give us carbon dioxide. Okay? So for each of these reactions we can associate some kind of extent of reaction, as we learnt in our earlier lecture, and these will be counted as two more variables. Okay? Now if you add up all these number of variables, then they add up to 20. Now after counting the variables, we have to count the number of independent equations correlating these variables. So let us now go for this equation counting. Now here we have put all the equations that are necessary for this. Now first we have the independent species material balances. They will count to 6. Okay, for each of the species, like you can see here that we have 1 plus 1 this methane, oxygen, nitrogen 3, then water 4, then carbon monoxide 5 and carbon dioxide 6. So we have 6 species involved in this particular process. So we are putting that for 6 of the species we have 6 species material balances. Now once you are writing the species material balance, there is no need to write the overall material balance. Okay? Now sum of species, as I was telling you, this will be counting to the total stream flow, and for these two streams we are having this total stream flow. Okay? Energy balance will always be 1, because energy balance is not done species wise, but it is done for the overall system. So it will always be counting to 1, and then specification of the values. Now understand this, these specifications, if you do not make these specifications, that means you can also do the degrees of freedom analysis without these specifications. Okay? So if you do not count this, then you will find that this total count will not be so. Okay? Now when you specify, what you are trying to do is that you are trying to reduce the degrees of freedom to 0, so that you can get some unique solution. Okay? So that is why we are doing this specification count. So here we have some specification. Please understand that the specified variables are not unique. The selection can be a user based thing. Depending on the situation, the specifications can differ. Okay? So this is one of the typical set of specified variables, I can say. Depending on the situation, you can also alter this set of the specified variables. Okay? For this particular set, as you can see that we have specified the pressures, temperatures, etc., and this oxygen to nitrogen ratio in the feed stream. And we are assuming complete reaction, the extent of reaction is implied for both reactions, etc. So all these things you will find that we have specified these variables. Okay? So if we specify this sort of variables and then we count these equations, then what we find, we are having these 20 equations. Now you can see that when we are doing the degrees of analysis, now we have to simply count the number of variables, number of independent equations, and then degrees of freedom is 20 minus 20, that is 0. Now 0 means we have a unique set of solutions for all the unknown variables in the problem. Okay? So every time whenever we want uniqueness, we have to make sure that the degrees of freedom is always 0. Next we come to another problem. In this problem, we have to estimate the adiabatic flame temperature. What it means is this: whenever there is some kind of combustion happening, now due to this combustion, you know that it will lead to some energy generation and there will be rise in the temperature. Okay? So this rise in the temperature can be estimated, and there are various methods. Now in adiabatic flame temperature, it means that word adiabatic means that it is assumed that there is no heat transfer between the systems and the surroundings, so that whatever heat is being generated by one particular reaction, that remains within the system, so that it can increase the system energy or internal energy of the system to the maximum possible extent. Okay? So that is the significance of the adiabatic flame temperature. So here we have to determine the theoretical flame temperature or adiabatic flame temperature for carbon monoxide gas burned at constant pressure with 100% excess air when the reactants enter at this temperature and this pressure. And this is the particular reaction. So this is the stoichiometric reaction which is given in terms of that for 1 mole of carbon monoxide getting combusted with half a mole of oxygen to give 1 mole of carbon dioxide, all in the gaseous state. Now please understand that whenever we are doing this kind of analysis, we are assuming that the outlet temperature pressure of the exiting stream is same as the reactor temperature. Okay, so that is why we are not counting the reactor temperature and pressure separately, and the same thing we did in our earlier problem too. We did not count the temperature pressure of the reactor separately from those of the outgoing streams. Okay. Now here we put all the conditions as given in the problem, and here we are assuming that the air to be a binary mixture of nitrogen and oxygen. Okay, even though air is not truly binary, but here we are assuming it to be true binary mixture, and in that case we take that conventionally we take the air to be composed of 79 mole percent of nitrogen and 21 mole percent of oxygen. So when you convert the mole percent into mole fraction, you get 0.79 mole fraction of nitrogen and 0.21 mole fraction of oxygen. Now here we have to find out the temperature at the outlet, and also we do not know the composition of the outgoing streams. Only thing is this, we know that this nitrogen which is going into the reactor will come out fully without any kind of reaction. Now what we do that, as we learnt earlier, we choose a basis. So here we are choosing a basis of 1 gram mole of carbon monoxide as our result in the problem statement is to be reported in terms of this particular quantity. Okay, and the reference temperature is taken to be 25 degrees centigrade and pressure to be 1 atmosphere, because as you know that the enthalpy is to be found from some reference values of pressure and temperature. So these are the two values of temperature, pressure based on which we are going to find out the enthalpy. So we write the balance equation here, and now what we find that 1 mole of carbon monoxide reacts with 0.5 gram mole of oxygen, and in the problem statement it says that we have sent 50% excess. So that means the actual amount of oxygen sent is the 0.5 is the stoichiometric amount into this 1 gram mole. This is the excess amount of oxygen we are sending. So total oxygen is this 0.5 gram mole, that plus the 0.5 gram mole, that is 1 gram mole. Okay. Now once we know the amount of oxygen sent into the system, then we can now calculate the amount of nitrogen entering into the system by knowing the composition of the air. So here we are writing that for 0.21 gram mole of oxygen we are getting 0.79 gram mole of nitrogen. So for 1 gram mole of oxygen, how much nitrogen will be sent? So this is the amount of nitrogen that is also entering the system with the air. Now we write the material balances, that these are the grammos of carbon monoxide, oxygen and nitrogen, and these are the various species at the outlet. And now from stoichiometry we can know how much of carbon dioxide, how much of oxygen and nitrogen are going to be produced. Okay, because we are going to make this one more thing, that in the exit we have 0.5 gram mole of oxygen, because another 0.5 gram mole has reacted with carbon monoxide. Okay. So after these material balances, now assuming that adiabatic condition, now we find out we have to find out the enthalpy of the reaction. So that we can find out the temperature, and we know that enthalpy of reaction is given by delta H out and delta H in, and in this case the in one we know because we can find out the total enthalpy change associated with each of the components, and here outside also enthalpy change associated with each of the components. So here this R is representing the total number of reactants and the P represents the total number of product species. Okay. Now we know that delta HI equal to HI minus HI25, that means this is the standard temperature for us. So with respect to the standard temperature, we are trying to find out the enthalpy change for ith species. And as we have derived earlier, that in this case we have to take the sensible heat, we have to take the heat of formation and the heat necessary for the phase change. Now with this particular thing, we know that this is the adiabatic, so we are putting this delta H equal to 0. That means delta H out is equal to delta H in. Now this is what we learnt earlier, that Cp may be given by this cubic polynomial, and here we have given you the A, B, C, D values for all the species. Okay, and here we say that the Cp is in kilojoule per kilomole Kelvin and temperature is in degree centigrade. Now next of the things are very simplified. I am not going into detail of this because I have done such a calculation earlier in the earlier lecture. So here we simply put this formula and find out the delta H, this sensible heat from this particular integration, and I have just put the final values after doing this integration here, and the total change in the enthalpy, as we learnt earlier, has to be found out by multiplying the respective amount of the number of moles of the species with the change in the enthalpy for that species, and for each of the species we have simply multiplied these numbers with number of moles to get all these things. So we are adding these two up and then we are multiplying with the number of moles. So we add these two up and multiply this mole, we add these two and get multiply with this number of moles. So after doing this, we are finding this is the total enthalpy change at the inlet stream, and then we know that there is no phase change in the system because all the species are in the gaseous phase. So we are putting this enthalpy change associated with the phase change as 0. And now we have all this information about the outlet stream, the standard heat of formation, and again these values are found from the data chart given in the literature. And now we are ready to find out the delta H out, and again we are putting all these. This is the final equation for the delta H out. It is similar to the one that is in delta H in. And what we are doing now, when we add up all these over the species, what we find, all these temperature terms can be brought out of the summation, and the summation is occurring for each of the components, for each of the parameters in the specific heat equation. So here you find all this summation represents the parameter in the specific heat equation, and these terms are representing the terms after the integration. So here I am not anymore going to detail, it is simply rearranging the two equations we have found out for these two enthalpies. So and next is this, we are finding that the final equation becomes a cubic equation in temperature, and so we are trying to solve an equation that is a function of temperature, and here we put the values of A, B, C, D, and now we find that we are using a Newton-Raphson method. So we have this derivative of the function. Newton-Raphson method I shall be teaching you in my subsequent lecture. This is one of the ways of finding the root of the non-linear algebraic equations. So we are putting this derivative of the Newton-Raphson method, and here we are putting the number of moles and standard heat of formation of all the components, and here this is the recurrence formula in the Newton-Raphson method. That means in this method what we do, that we take some assumed value and keep on updating the value in terms of the function value and the derivative of the function. So I am not going to detail of this particular method, I shall be taking them up later. So to suffice to say is this, that here is we put some kind of convergence criterion, and this k represents the number of iteration. So basically we are checking the values in the two consecutive iterations. Just a small modification here will be that these T's are calculated at the kth temperature. So at the kth iteration level. Okay. So, it is as you can see, this is for kth iteration level. So, at the same temperature we will be calculating this the function value and the derivative of the function. Okay. And then for checking the convergence, the user puts some kind of convergence criterion. It could be 1%, 10% or 0.1% depending on the accuracy needed. So, we put that criterion here and then we get some convergence, and if you solve this equation you will find the approximate value of the theoretical flame temperature or adiabatic flame temperature is going to be this value. Okay. So, this is a pretty simple way of putting this applying the energy balance, because in the energy balance we are assuming the change in the kinetic energy, potential energy to be 0, the adiabatic means Q to be 0, and there is no work done because the reactor is a fixed reactor, rigid reactor. Okay. So, when in the energy balance equation, when we drop all those terms, we will find that we are having the terms which were shown in this particular solution. Now, we go to the next problem. In this problem, we are applying the same energy balance equation, but for multiple reactions. So far we have looked into one reaction, now we are going for multiple reactions. In this we have the combustion of limestone. Limestone is calcium carbonate with natural gas, that is methane primarily, in the presence of 50% excess air produces calcium oxide, that is CaO, and calcium carbonate enters the process at 25 degrees centigrade and calcium oxide exits at 900 degrees centigrade. Methane enters at 25 degrees centigrade and the product gases exit 500 degrees centigrade. So, we have to determine the amount of calcium carbonate produced per gram mole of methane combusted. Okay. So, with this problem statement, now we show you schematically how this thing looks like. So, here we have the incoming stream of calcium carbonate. Okay, this is a kind of kiln in which this reaction is going on, and here we have written the conditions of the calcium carbonate as given in the problem, and here we show it 100%, that is, it is taken to be pure calcium carbonate, and this is the number of moles of calcium carbonate, and the other inlet stream is the methane here, and all the conditions for the methane are also given here. It is pure methane, the natural gas, it's primarily methane, but here we are assuming that it is pure methane stream. And when we have shown the product streams over here, we are showing this thing on this left hand side because calcium carbonate is solid. So, by gravity it will come down, and similarly this calcium oxide is also solid. So, it is will be taken from the bottom of the kiln. On the other hand, any kind of gases will move up due to buoyancy and they will be collected from the top of the particular reactor. Okay, so, they have been shown on the top. Okay, and similarly this gaseous inlet stream is also shown from the bottom because it will tend to move up the column. Okay. Now, along with methane, we are also sending the air, and again we are assuming the air to be a binary mixture of nitrogen and oxygen, and nitrogen is taken to be 0.79 mole fraction and oxygen taken to be 0.21 mole fraction. Now, the assumptions are the process occurs at 1 atmosphere and 25 degrees centigrade, system is adiabatic, so Q is 0, and neglecting other terms like change in kinetic energy, change in the potential energy, and there is no work done. So, we shall be arriving at the total change in the process will be simply the change in the enthalpy of the product stream and minus the change in the enthalpy of the raw materials. So, taking the basis as this 1 gram mole of methane, we write for the species the molecular weight, the heat capacity taken from the literature, and these are the two reactions. Okay. One, in the first reaction we find that calcium carbonate is going into to decompose into calcium oxide and carbon dioxide, and in the second reaction what we are finding that methane is combusting with oxygen to give carbon dioxide and water, and these are at 500 degrees centigrade, and this calcium oxide is at 900 degree centigrade. And here you see that with this kind of balances, we have also put the number of moles of oxygen and nitrogen entering the system. So, 1 mole of methane requires 2 gram mole of oxygen, as you can find from this stoichiometric equation. And again we have been told that we are sending 50% excess air. So excess, that means that 2 gram is needed and we are putting excess of this, that is 1 gram mole is excess, and that is total amount of oxygen going into the system is 3 gram mole. Okay, and once we know the amount of oxygen going, so we can find out the how much nitrogen is going into the system, and we can find out the gram mole of nitrogen going inside the system. Now we write the species material balance to find out the number of moles of each of the species. So here I have shown you for the inlet stream for all each of the individual species over here, okay, and here I have shown you for all the outgoing streams here. So here I am doing the elemental balance, as I told you that in this case elemental balance will be better, because we are just trying to find out that how much carbon is going inside the system, how much carbon is going out of the system, and we are not going to go for the delta H reaction, that is the heat of reaction. So we are going with the elemental balance. So after this what we are doing, that we put all these values from the literature, heat of formation, sensible heat, and sensible heat as you know that we have found it out by the integration of the CPdT, and this is the total heat change for the all the streams, for the output streams, and these are pretty straightforward, and since I have explained these things to you in the earlier problem, so I am not going into detail of these. Once you know the temperatures of the various streams, you can find these particular values very easily by integrating from 25 degree centigrade to these temperatures, and then afterwards you are just simply adding these two and multiplying with the number of moles, and now you get this kind of output things. Now here you see that once you put for the input and output, then you find that there are many of these things are unknown. Okay, so you have to know the number of moles of carbon dioxide, you have to know the feed stream velocities. So whatever equations we have written earlier, and what we are just rearranging the equations to get the solution for each of the unknown variables, and this is very straightforward. Basically you are solving a few coupled linear algebraic equations. Okay, so I am not going into detail of this solution also. You can do it very easily, and ultimately you find that you are getting these two values. Once you get these two values, now you can find out that how much calcium carbonate is being consumed per unit gram mole of methane by this particular formula. Okay, so this is very straightforward problem. So more details you can find out from these two books. Thank you.